Today, we're pulling back the curtain on two of the most important components in all of electronics, inductors and capacitors. Seriously, these things are the hidden workhorses inside pretty much every gadget you own. Let's dive in. So, think about this for a second. What on earth could connect that clunky power brick for your computer with the super sleek, high-tech screen on your phone? They seem like they're from two totally different worlds, right? Well, the surprising answer is all about how they store and control energy. And by the end of this, you'll see exactly how it all connects. All right, to get this, we need to think a little differently. Now, most of us have heard of resistors, the little guys that act like speed bumps for electricity and get hot because they waste energy. Well, inductors and capacitors are playing a completely different game. They aren't about spending energy, they're all about saving it for just the right moment. This really gets to the heart of it. A resistor's job is to burn off electrical energy as heat. That's it. But inductors and capacitors? Think of them more like tiny, ultra-fast rechargeable batteries. They grab onto energy and hold it, ready to release it exactly when and how the circuit needs it. Okay, so if they both store energy, what's the big deal? Why do we need two different kinds? Well, it turns out they're like two sides of the same coin. They're a perfect pair that stores energy in ways that are fundamentally different, but equally important. And here it is. This is the core difference right here. An inductor, which is really just a fancy coil of wire, stores its energy in a magnetic field that builds up around it. A capacitor, on the other hand, which is basically two metal plates with a tiny gap, stores its energy in an electric field between those plates. Magnetic versus electric. That's the whole shebang. Let's put a quick definition on it. The inductor, which we symbolize with the letter L, is a passive component that, as we said, stores energy in a magnetic field. And we measure its ability to do that, its inductance, in a unit called the Henry. Yep, Henry, or just H for short. And its partner in crime, the capacitor, gets the letter C. It stores its energy in that electric field. Its capacity to do so is called capacitance, and we measure that in farads, or F. Now check this out. The math behind them actually tells the whole story. Look how similar these formulas are. It's kind of beautiful. For the inductor, the energy it holds depends on its inductance, L, and the square of the current flowing through it. But for the capacitor, it's all about its capacitance, C, and the square of the voltage across it. This is so important to remember. Inductors care about current. Capacitors care about voltage. Okay, so we know what they do. But the real magic isn't just that they store energy. It's the strict rules they follow while they're doing it. Understanding these rules of the road is what makes them so incredibly useful. If you remember one thing about inductors, make it this. An inductor hates change. Specifically, it hates changes in current. Because its whole identity is wrapped up in that magnetic field created by the current, it will fight tooth and nail to keep that current flowing steadily. Trying to change it instantly would require infinite voltage, which just isn't possible, so the current has to be smooth. So, what happens in a really simple DC circuit where the current is just cruising along nice and constant? Well, if the current isn't changing, the inductor has no reason to fight back. It just chills out. It basically becomes invisible and acts like a plain old piece of wire. In engineering terms, we call that a short circuit. And now for the capacitor. You probably guessed it, it has its own golden rule, and it's the perfect mirror image of the inductors. The voltage across a capacitor cannot change in an instant. Why not? Because to zap its voltage from one level to another in zero time, you'd need an infinite rush of current. Again, not going to happen. So voltage has to be smooth and continuous. And the result in that same DC circuit? Well, once the capacitor fills up with charge and its voltage is steady, that's it. It's full. No more current can flow through. It acts like a roadblock, a break in the wire. We call that an open circuit. It just sits there, holding its energy.
So we know how they work on their own. But in real electronics, you rarely just have one. So what happens when you start stringing them together? Well, just like resistors, we can combine them, but the rules for how they add up have a fascinating little twist.
Here's the cheat sheet, the really easy way to remember this. Inductors, they're straightforward. They combine exactly like resistors do. No surprises there. Capacitors, though, they're the rebels. They do everything backwards compared to what you'd expect. And you can see it all laid out right here. Look at the inductor rows. See? The formulas are identical to the ones for resistors. Series? Just add them up. Easy. But now, look at the capacitors. It's totally flipped on its head. They add up directly when they're in parallel, and you have to use that tricky reciprocal formula when they're in series. It feels weird at first, I know, but getting this down is a huge step in designing circuits. All right, theory time is over. Let's bring this all back to our original question. That power supply and your phone screen. Well, that incredible responsive touchscreen that you tap and swipe on all day long, it works entirely because of the principle of capacitance. Right underneath the glass on your phone, there's an invisible grid of super thin wires. This grid creates a constant, stable electric field all across the screen. We call this a field of mutual capacitance. And your phone is just sitting there, constantly monitoring this field, making sure everything stays exactly the same. It's a pretty genius three-step dance. First, the grid creates that baseline. The phone knows exactly what the capacitance should look like at every single point on the screen. That's normal. Second, you come along. Your finger is conductive, and when you touch the glass, you actually mess with that little electric field right where you're touching. You change the local capacitance. And finally, boom, the phone's controller instantly sees that change, pinpoints its exact coordinates on the grid, and registers it as a touch. So let's bring it all home. The inductor in your power supply is fighting changes in current to give your laptop clean, stable power. And the capacitor grid in your phone is sensing tiny changes in an electric field to register your touch. This ability to store and release energy in these invisible fields, it isn't just a neat trick. It is quite literally the foundation that makes almost all of our modern technology possible. I mean, just stop and think about that. We harnessed an invisible force field so that we could physically interact with our digital world. It's incredible. And it really makes you wonder, doesn't it? What other invisible forces are all around us, just waiting for a clever bit of engineering to be harnessed next?